Good afternoon, this is Dr. Pradhan here. Welcome to NPTEL project on econometric modeling. So, today we will continue the reliability part of bivariate econometric modeling. In the last class we have discussed the need of reliability and the structure of reliability for the bivariate estimated econometric model. So, now we like to highlight this same issue again here, because some of the things we have not discussed last class. So, the thing is for two variables y and x. So, our fitted model is like this: y hat equal to alpha hat plus beta hat x. Okay. So, now the essential point is here we have two specific objectives. The first objective is to know the significance of the parameters, and second objective is to know the overall fitness of the models. Okay. So, in this particular, so far as the reliability is concerned, so we have two specific objectives. So, first objective is to know the significance of parameters, okay, and that is with respect to alpha hat and beta hats. Okay. And second, the significance of overall fitness of the model. Okay. Overall fitness of the model. So, we have two specific objectives so far as the reliability is concerned. So, first objective is to know the significance of the parameters, that is the weightage of each parameters. When we fit the regression equations with respect to x and y, and obviously the impact can be negative or the impact can be positive, okay, which is judged through the slope of the x coefficient or x variables. This which we have to judge through slope of the x variable, that is nothing but beta coefficient, and alpha coefficient is just to know the significance of the supporting component factors. So, now in just to put it in a straight line equation, and this is intercept and this is what we call it a slope. So, now we like to know whether this intercept or the supporting component is a significant one for influencing y, and whether x component is a significant one again for influencing y. So, now to know this one, so we have standard procedures. So, that part the discussion of this part particularly is known as the reliability of this estimated model. So, before we track this first objective, that is the significance of the parameters. So, the significance of parameter is that, so we have to represent the estimated models in a typical tabular form, so that we can understand the exact structure of the reliability. So, now when we have estimated models, we had y hat equal to alpha hat plus beta hat x. So, then the standard table we have to design is here. So, we have estimated parameters, okay, then second the estimated values, okay, then third column represents variance of estimated values, then standard error, then t statistics, then probability, okay, probability level of significance. These are the structure of this particular significance of the parameters, that means with respect to the first objective. So, what are the estimated parameters for this particular bivariate setup? The estimated parameters, first parameter is related to alpha hat, and second parameter is beta hats. Okay. So, this is what the means. Now, this table is altogether complete ones. Okay. So, this is what we have to design this entire tables. All right. So, now so this particular structures. So, what is estimated value? Alpha hat we will get it this is nothing but y bar minus beta hat x bars, and beta hat is equal to summation x y by summation x square. So, which we have discussed long back. So, now variance of estimated alpha, that is nothing but variance of alpha hat, and this is nothing but variance of beta hat. Then standard error of beta, that is nothing but variance of alpha hat, and this is square root of variance of beta heads. Okay. So, this is how the standard error will be designed. So, t statistic for this is t alpha head and this is t beta heads, and we like to know what is the significance levels. Okay. So, now this model is theoretically is okay, but technically or practically, so far as the significance of the parameter is concerned. So, we have to evaluate in a proper sequence, and that has to be compared with the tabulated value, which we have discussed details in the last class. So, now what is all about this variance of alpha head. So, basically the variance of alpha head is derived. There are technical procedure how you have to get the variance of alpha head, but in the meantime variance of alpha head is nothing but sigma square u into summation x squares divided by n summation x squares. Okay. So, here this is this particular item is a capital X and this particular x is a small x. So, this is nothing but deviation format. This is what we can represent in x minus x bars. All right. So, now altogether there are 4 items. So, sigma square u summation capital X square, then n into summation small x square. Okay. So, this is nothing but variance of variance of x. So, the question is what is sigma square here. So, sigma square u is called as a error variance here. So, this is otherwise called as a error variance. Okay. Error variance, the way we are calculating the variance of a particular variable, say x or particular variable y. So, we have to also calculate the variance of, you can say u or e, because in a bivariate setup we start with the 2 variables y and x, but ultimately we with the help of estimated model we get to know the or we have to create another variable called as a u or otherwise called as a error terms. So, now altogether when we have a fitted models, then the entire system consists of 4 important columns. So, first column is related to y column. So, it gives the information about y structure, and we can get to know what is the variation of y, or you can say standard deviation of y or mean of y. So, these are the descriptive statistic we have to draw from the y column. Similarly, in the x column, so we have series of x information corresponding to all y component. So, we can also get to know the entire descriptive statistics of x variable. So, now next to x, then we start with a variable called y head. Y head is nothing but alpha head plus beta head x. So, now with the help of alpha head value and beta head value, and with the help of x information, then we can create the y head columns. So, y head column also we can get this descriptive statistic of y head, because y head altogether here another variable which is designed through the help of y and x and the estimated parameters alpha head and beta heads. So, now with respect to y head and y, we have to create another columns called as a error column. So, that is represented as a u columns, or you can say e column. So, now corresponding to every figure of y head and y, so we have to find out the error component. For instance, u 1 is equal to y 1 minus y 1 head. Similarly, e 2 equal to y 2 minus y 2 heads. So, the difference between the estimated y and actual y. So, this will give the error representation. So, now once you have error series starting from u 1 to u 1 e n, provided the system is nth observation, then you have to calculate the error variance. So, this error variance it is called as a sigma square u. So, sigma square u sometimes this error variance we will represent here summation e square by n minus 2. Okay. This summation sigma square u equal to summation e square by n minus 2. Here basically this particular summation e square by n minus 2, we can put it in other way, summation e square by n minus k. Actually, k is the number of variables in this particular systems or number of parameters in this particular systems. So, now since this particular model is a bivariate one, so obviously there are 2 variables and there are 2 parameters that is alpha parameters and beta parameters. So, as a result k is represented as a here 2. So, there is no point to write summation e square by n minus k, because it is already known to us that k represents the total number of variables in the system, that is you can say y and x, or number of parameters in the systems, that is alpha head and beta head. So, now but when there is a multivariate system, then this particular terms can be represented as a summation e square by n minus k. for instance, if we have a trivariate models, then obviously summation a square by n minus 3, because there are 3 variables in the system. Similarly, we have to extend one after another, then obviously the n minus k component will start, you can say, expanding. So, now sigma square e equal to summation e square by n minus 2, where summation e square is equal to summation y hat squares plus summation y hat square, okay, no, this is summation y square minus summation y hat squares. So, that means in other words, it is nothing but summation y square minus summation y hat square. Let me explain how it is happened here. So, this is usually derived in a technical procedures. So, the details calculating procedure of this particular terms we can analyze here. Okay. So, now this particular system say, let us say we have a system, say y equal to y hat plus e. Okay. So, this is how we start the process. So, what we will do, we call it equation number 1, then we you can say subtract y bar on both the sides. Okay. So, this is nothing but y hat minus y bar, so plus e. Okay. So, now you see here. So, the actual representation is like this. So, now this is what we call it the x series, and this is what we will call it y series. Okay. So, then we have a estimated corresponding to y. So, we can get the, you can say we can get the y y bar, and corresponding to x we have to get the x bar. So, this is what we call as a mean of y, and this is called as a mean of x. So, now with respect to y and x information, our objective is to get the estimated line, that is called as a best fitted line. So, now let us assume that this best fitted line can be represented like this. So, this is y hat, which is equal to alpha hat plus beta hat x. Okay. Beta hat x. Okay. So, now this particular point is very relevant, because in this particular point where y hat bar or exactly equal to y bars. Okay. So, this is how we are representing here. That means, this entire representation we can write it here like this: y minus y bar is equal to y hat minus y hat bars plus e. Okay. Because y bar and y hat bar is equal at that point of equilibrium. So, it is not a issue. So, what we have to do, instead of writing this one, so we call it, this is small y, okay, in deviation format, and this is what we will call it y hat in a deviation format, and this is e, this is in also is as usual okay, error terms. So, now this is what we have derived from here. Okay. So, now put it in a proper way. So, it is y equal to y hat plus e. Okay. So, now what we have to do, so this is original equation, we have y minus y equal to y hat plus e, this y and this y hat is in a capital format, and this y and this y hat is deviation format. So, there is a huge difference between this deviation and actual. So, now we have transferred the actual to deviation format. So, for this simplicity is concerned. So, now what we have to do, we have to apply summation. We first apply square in both the sides, and then we have to apply the summation to get the entire structures. So, now what we have to do, if we do that, then the entire structure becomes summation y square equal to summation y hat plus e whole square. So, obviously, I equal to 1 to n here, this is I equal to 1 to n, because I represents the sample units, it will start from 1 to n. Okay. So, because we are in the process of cross sectional modeling and our sample unit represent here I. Okay. So, now so obviously, I equal to 1 to up to n. All right. So, now what you have to do, so this this particular component y hat head bars. So, this is what we can write in the format like this: y hat squares I equal to 1 to n plus summation e squares I equal to 1, okay, plus 2 summation y hat into e. Okay. So, this if we expand this particular right hand side of this equation, then we will get summation y square equal to summation y hat squares plus summation e square plus 2 summation y hat into e. but this particular term is exactly equal to 0. Okay, this particular term is exactly equal to 0. So now the question is how it becomes 0. So let me explain here. Okay, so the structure is here. So our point is here to prove that summation y hat e equal to 0. Okay, so first of all, what is y hat? Y hat is equal to some y hat minus y hat bar. Okay, so this is nothing but y hat minus y bars. All right. So now if we will simplify, then it is nothing but alpha hat plus beta hat x minus alpha hat minus beta hat x bar. Okay, again if we will simplify, then it is nothing but alpha hat cancel. So beta hat into x minus x bar, so which is equal to beta hat into small x, that is what we call it deviation. That means this particular item is a small x. Okay, so this is one part of the problem. Then e equal to y minus y hat. Okay, so that means e equal to y minus y hat, which is nothing but y minus beta hat x. Okay, beta hat xi. Okay, so now this is y e and this is y hat. So now we have to integrate. So now summation y hat e is equal to summation, because this is summation here. So this beta hat x into y minus beta hat x. Okay, so obviously this is xi and this is xi, this is yi. So like this. Okay, so of course I equal to 1 to n, and this side I equal to also 1 to n. Okay, the actually the term is 2 into summation y hat into e, but if we prove that summation y hat equal to 0, then obviously 2 into 0 equal to 0. So now what we have to do, so here just we take beta hat common. So then summation xi yi, okay, minus minus beta hat is common here. So beta hat summation x squares. Okay, summation x squares, beta hat summation x squares. Okay, and then this beta hat is you can say we have taken a common beta hat. So then it is nothing but beta hat into summation xi yi minus what is beta hat? Beta hat is nothing but summation xi yi divided by summation x squares. Okay, so we have again summation x square. So this summation x squares, this summation x square cancel. So that means equal to beta hat into summation xi yi minus summation xi yi. Okay, so summation xi yi. So this and this is cancelled. So that means it is nothing but beta hat into 0, which is nothing but equal to 0. All right. So now, so that means the entire structure is like this. So beta hat equal to summation xi yi. We are just expanding the beta hat value here. So obviously summation x square cancel. So the left out term is summation xi yi. So obviously summation xi yi is here. So this is summation xi yi. So that means it is equal to 0. So now we have proved that summation y hat equal to 0. So now you come to this stage here. So summation, that means summation y square is equal to summation y hat square plus summation e squares. Okay. So now we will start our process here. So what is exactly this particular funda? So this particular funda is like this. So we start with, you can say, y equal to y hat plus e, then we transfer into y equal to y hat plus e, then after doing some process. So we get to we have received summation y square equal to summation y hat square plus summation e squares. Okay, so this is I equal to 1 to n, and this is I equal to 1 to n, and this is also I equal to 1 to n. Okay. So this is how the entire structure is all about. So that means our point is here to justify the significance of the alpha parameter and beta parameters, and to judge this particular task. So we need to have variance of alpha hat, and to have variance of alpha hat and to have variance of beta hat, we need to integrate with again with the error variance, because this particular variance of alpha hat depends upon the variance of error variance, and again for you can say variance of beta hat we need also error variance. So, we like to know what is the exact component of error variance. So, expanding by this process. So, we are in the stage that summation y square equal to summation y hat square plus summation e square. This particular term is called as a TSS, and this particular term is called as a ESS, and this particular term is called as a RSS. Okay, this particular term is called as a RSS. So, what is exactly this particular term? So, that means this is called as a total sum square, this is explained sum square, and this is called as a residual sum square. So, that means this is what we call as a total sum squares, then this is explained sum squares, and this particular term is called as a residual sum squares. Okay, sum square. It is otherwise known as unexplained sum squares. Okay, this is otherwise called as a unexplained sum square. This is otherwise called as a unexplained sum squares. All right, this is otherwise called as a unexplained sum squares. So, now what is exactly this particular term? So, this is nothing but summation y minus y bar whole squares I equal to 1 to n, and this particular term is nothing but y hat squares. This is nothing but summation y hat minus y bar whole squares I equal to 1 to n. Then this is nothing but summation you can say y I minus y hat whole square I equal to 1 to n. In fact, the entire process we started from here only, because our entire model is nothing but e equal to y minus y hat, and the way we are minimizing the error sum, we have received the alpha hat component and beta hat component. So, now to justify the significance of this particular parameter alpha hat and the parameter beta hat, we again come down this particular process. So, now we have to explain how this means there is lots of interesting facts behind this particular structure. So, let us see how is this particular structures. All right. So, now we have the component summation y square equal to summation y hat square plus summation e square. So, that means what we can conclude, total sum square is equal to explained sum squares plus residual sum square. All right. So, we are now in a position to say that total sum square is equal to explained sum square and residual sum squares. The way I have highlighted earlier, that you know, when you have y series and we have x series, that is our you can say beginning. So, we have y information and we have x information, and through the process we have received the error component. That is how you can say it is all about you can say statistics or econometrics. So, that means we like to verify that whether x is totally influencing the y component or x is partly influencing y. Okay, and so some of the other part can be explained in other way. For instance, if x is not 100% influencing y, then obviously there is some point of lacking. So, that lacking part we have to discuss, and that is nothing but it is called as a residual. So, that means when we have y series, we like to know what is the total sum square, that is nothing but sum of y I minus y bar, the deviation and its squares. That means the variation from all these points to the you can say from the arithmetic mean. So, now total sum square is equal to explained sum square, that is nothing but summation y hat minus y hat bar squares, and rest is summation e squares, that is residual sum square. So, now put it in technically. So, what I will do, let's assume that this is equation number 1. So, what I will do, I will divide summation y square both the sides. Okay. So, dividing summation y square on both the sides of equation 1, then what we have. So, you see here, so summation y square divided by summation y square is equal to summation y hat square by summation y square plus summation e square by summation y square. All right. So, now this particular term is exactly equal to 1. Okay. This is equal to 1. Okay. So, now we this is one component and this is another component. So, that means 1 equal to summation y hat square by summation y square plus summation e square by summation y squares. All right. So, this is how means we are in a position to draw like this. So, obviously, I equal to 1 to n here, I equal to 1 to n here, this is I equal to 1 up to n years. All right. So, now we have two parts. So, we call it, this is part A and this is we call it a part B. Okay. Let us first expand what is this part A component. So, part A component is like this, summation y hat square by summation y squares. Okay. What is y hat exactly? So, y hat is nothing but summation small beta hat means beta hat and small x. Okay. This is whole square I equal to 1 to n divided by summation y square, obviously I equal to 1 to n. All right. So, now what is beta? That means what is, if we will simplify further, then it is nothing but beta hat square then summation x square divided by summation y squares. All right. So, now what is beta hat? So, beta hat, actually beta hat is equal to summation x y by summation x square. Okay. Beta hat by beta hat equal to summation x I by summation x square. Okay. So, now you see here, if you simplify further, then what we can do. So, summation put it here. So, summation, okay, I will write it here again. So, summation y hat square by summation y square is equal to summation x y whole square divided by summation x square whole square into summation x square, okay, divided by summation y square. Okay. This is what y hat square by summation y square. So, now you see here, this is summation x square and this is summation x square to the power again 2. So, this is how it is cancelled. So, that means it is nothing but summation x y whole square by summation x square into summation y square. All right. This is the left out term from this component. So, that means this is what we have received from the part A. So, part A, if we will expand this part A, that is the variance of explained ratio between explained sum square to total sum squares. So, when means the exact term is summation y square equal to summation y hat square plus summation e square, that means the total sum square equal to explained sum square plus residual sum square. So, now what we have done, so we divide the total sum square both the sides. So, then the left side of this problem is equal to 1. So, then right part of the first part is the explained sum square divided by total sum square. This is how it is called as a ratio between the explained sum square to total sum square, then the ratio between residual sum square to total sum square. So, now we like to know if we have a component explained sum square to total sum square, what is that issue, and if the ratio component is the residual sum square divided by total sum square, what is that component. So, then we have to now interpret accordingly. So, now by this process we are in the process we are coming to a position that summation y hat square by summation y square, that is nothing but ESS by TSS is nothing but summation x y square by summation x square into summation y square. This is what we call it is just like R squares. Okay. This is what we call it R square. That is, what is R square? R square is nothing but square of correlation coefficient. Okay. This is what called as a correlation coefficient. You see, what is correlation? Then correlation is simply nothing but covariance of x y divided by sigma x into sigma y. Okay. If we will simplify further, then it is nothing but summation x minus x bar into y minus y bar divided by n all divided by summation x square by n square root, then summation y square by n square root. Okay. So, this n cancel, all right. So, now if this is r component, this particular component is nothing but summation x y. Okay. This is summation x y divided by summation x square into summation y squares, all right. So, now if we will make it square, then obviously r square equal to summation x y whole square divided by summation x square into summation y square. Okay. So, what we have received from here only. So, that means this particular ratio explained sum square to total sum square is nothing but the r square component. What that means, what is r square here? R square represent the square of correlation coefficient, but you know this particular component is very much true when we are in the bivariate process, but when there is a multivariate process, then the ratio between explained sum square to total sum square cannot be represented as a simple correlation coefficient. That is something different. What is this difference? The difference is actually this particular r square component is represented as a coefficient of determination. Okay. So, this particular component, this r square component is represented as a coefficient of determination. This particular item is represented as a coefficient of determination. So, what is this coefficient of determination? A coefficient of determination, that means you see here we have here y square is equal to summation y square equal to summation y hat square plus summation e squares. So, that is what we have received 1 equal to summation y hat square by summation y square plus summation e square by summation y square. Okay. This is what we have received, and by the process this is otherwise known as ESS by TSS, and this is what we have RSS by TSS. Okay. So, now this particular component by the by the process of derivations, what we have received, it is nothing but simply you can say r squares. Usually when we will represent the coefficient of determination, then it is nothing but represented as a capital R square. So, what we have written earlier, it is called as a small r square. So, that means small r square and capital R square both are same in the case of bivariate model. So, bivariate model in the that means in the case of bivariate model, the coefficient determination and the square of correlation coefficient are similar. So, that means they are same, but the interpretation is somewhat different. In the correlation coefficient, what we have studied the association between the two variables, degree of association between two variables. So, now here r square, capital R square, we have judged through the ratio between explained sum square by total sum square, and explained sum square is nothing but total sum of the x component, okay, that is explained items, and divided by total sum of y component, okay, which is nothing but dependent component. So, now we like to know what is the percentage influence of independent variable to dependent variable, or explanatory variable to explained variable. That is what we are now in the process. So, that means r square is the ratio between explained sum square to total sum square. By default, it is equal to 1 here plus RSS by TSS here, okay, RSS by TSS here. So, now there are beautiful interpretation here. So, what is this beautiful interpretation? Fortunately, this particular item can be again turned into this one. So, now we know correlation coefficient is usually in between -1 less than equal to 1 Okay. So, this is how the correlation coefficient range. Okay. This is correlation coefficient range. Okay. This is correlation coefficient range. All right. So, now like correlation coefficient range, r square is always in between 0 to 1. Okay. So, this is the range of coefficient of determination. So, what is the coefficient of determination? It is the ratio between explained sum square to total sum square. Means technically, or you can say if you go by physical interpretation, it is the variation of total variation of explained items to, you can say, total variation on y. So, this is how it is called as a r square or coefficient of determination. So, coefficient of determination is nothing but percentage or proportion variation of y, which is explained by the proportion variation of x. Okay. This particular term is called as a proportion variation of y, which is explained by proportion variation of x, and this particular component is represented as a proportion variation of y, which is explained by proportion variation of y. That means, this is total sum square is nothing but y square. So, this is our total component. So, we like to know what is the x influence on y and what is e influence on y. So, that is why it is known as a proportion variation of y. This is proportion variation of y, which is explained by this proportion variation of x, because ESS is the entire component of ESS depends upon the x component only. Then this is nothing but proportion variation of y, which is which is not explained properly, that is what we call as a RSS. That means, that will taken care by u component. So, 1 equal to r square by r square plus RSS by TSS. Now, so we have the range 0, r square and 1. So, this will give you the model signal. This will give the reliability of the model signal, so far as the second objective is concerned. So, now you see, we start with the first objective, and by default we are now going to explain this second objective. So, that is the overall fitness of the models. So, now the moment we will get r square, there is a proper structure how you have to receive this r square and how you have to go for its statistical level of significance, because so far a first objective is concerned with respect to alpha hat and beta hat. So, we are applying the t statistics. So, now when we are going for overall fitness of the models, then we have to use the f statistics. So, now we are just explaining how we are receiving the error variance and how it has connected to total variance of y and total variance of x. So, now by this process we like to now explain how is the structure of this significance of the individual parameters, that to alpha hat and beta hat, and in the other side by means by using all these TSS, ESS and RSS, we like to explain how the overall fitness of the model will be statistically significant. So, that means, we have two clear cut objectives in our mind. First is the significance of the parameters and the significance of the overall fitness of the model. So, before I highlight the entire structure of the r square significance level and the typical parameter significance level, so we like to highlight here the influence of r squares, because the value of r square always in between 0 to 1. So, if it is 0, how is the structure, and if it is 1, how is the structure. So, let us see here. So, now r square, so the entire component is r square plus summation e square by summation y square is exactly equal to 1. Okay. So, now this is how we have observed. So, now since this is our target, so what we will do, we will take r square equal to 1 minus summation e square by summation y square. Okay. This is what we have received from this simplification. So, what we have to do here. So, now let us say if case 1, if r square is equal to 1, then what will happen. So, if r square equal to 1, this particular item is equal to 0, this particular item exactly equal to 0. So, r square equal to 1 means this is equal to 1 and this particular item is equal to 0. So, that means, the model is absolutely fit for this, you can say, problem. So, the when r square is 1, then it is the best fitted models. Okay. So, now when r square exactly equal to 1, then the unexplained component, the percentage of unexplained component is exactly equal to 0. That means, there is no way u has a impact on, you can say, y variable. So, that means, the 100% influence of x on y. So, this is how the this is the case when r square exactly equal to 1, but in real life situation or real life problem, it is very difficult to get a situation when r square exactly equal to 1. All right. So, in the other side, when r square equal to 1, then it is called as a complete fitted or perfectly fit models. This is what we will call as a perfectly fitted models, but this is not the sufficient conditions. This is the necessary conditions. The when r square equal to 1, the overall fitness of the model is very high, or very high means it is a excellent one. So, that means it is completely fitted models, estimated model. So, it can be used for forecasting and policy use, but the sufficient condition is that when r square is exactly equal to 1, then corresponding to the first objective with respect to significance of the alpha hat and beta hat, it has to be significant, highly significant, then the model we can say that it is a best fitted model. Otherwise, if r square is exactly 1 and model is the significance of the model is absolutely high, and the other side, if the parameters are not statistical significant, or few parameters are statistical significant and other parameters are not statistical significant, even significant at a very lower level, then the model cannot be used as a forecasting, even if r square equal to 1, because we are just in the beginning of this process. When we have r square equal to 1 and parameters are not, all parameters are not statistically highly significant, then there is a serious problem in the modeling. So, there will be some complex problem in between. So, that complex problems we have not highlighted, we will highlight details when we will proceed, when we will proceed accordingly. So, we like to know a later stage, not now. So, what we can now you can explain that when r square equal to 1, just we interpret that it is perfectly fitted the models, keeping other things remain constant. Okay. So, now case 2, when r square is equal to 0, then the model is completely unfit, that means, the entire variations we will receive from u only. So, that means, this particular item is equal to 1 and this is equal to 0. So, now when r square equal to 1, so that means, this is equal to 0. When r square equal to 1, then summation y square is equal to summation y hat squares. Okay. This is summation y square equal to summation y hat square. When it is unfit, then summation y square is equal to summation e square. All right. But this is rare and this is rare. So, why it is rare? It may not be rare, but this is very extreme situation. The reality is that when we are in the process of fitting a model, then obviously we must have some theoretical knowledge. So, when we have a theoretical knowledge, then obviously means most of the instances r square cannot be equal to 0. It may be very low levels, but it cannot be 0. If your r square value is coming 0, that means your theory is not absolutely okay. That means, your identification of problem with relate to all variables are not systematically okay. So, there is some kind of problem. So, that is why before going to fit these particular models, your theoretical knowledge must be very perfect, and you must be in a position to identify exactly the structure of variables. If your initial homework is very tough, then obviously later stage of modeling will not face problems. Otherwise, it is just like a continuous process until you get the best fitted models. If you do not go stepwise process, then obviously every time we will go back to again original position till you get the better fitted model. So, that is why each and every stage should be perfectly okay before we going to next stage. So, in reality we have r square one extreme equal to 1 and another extreme r square equal to 0, but it is very exceptional and it is also very exceptional. So, what is the actual? actually is when R square value is close to 1, then it is called as a best means better fitted models. We cannot say best fitted model. When we will call is a best fitted model, then obviously R square equal to 1. So, now when R square is close to 1, then it is called as a that means the fitness of the model will start increasing. That means you start from R square equal to 0.0, 0.01, 0.02, 0.03, 0.04, 0.5 like this. So, you will go up to 0.09. So, now we have 3 different ranges in fact, you see here. So, the range is like this. So, take a case here. So, this is what we will call 0, then 0.1, 0.1, then 0.2, then 0.3 like this, then this is 0.5, then of course, this is 1.0. This is how the R square ranges. This is the R square range. So, when we will call it R square 0 less than 1, so the range will be like this. So, this is middle. Okay. So, now if you are in this stage, the model fitness or model accuracy will be start declining. When we are moving this side, then the model accuracy will be start increasing. So, now always our objective is to go this side, not this side. So, that the model fitness or overall fitness of the model will start increasing. So, now when your R square value will be close towards 1, then it is the signal of, or it is just like a green signal, it is the outcome of the best fitted models. So, when we are closing to 0 or close to 0, so then obviously it will give you the red signal. That means we are diverting from the best fitted model. So, we should not go towards the red signal, rather you have to go towards the green signal, where the best fitted model or the model accuracy will be start increasing. So, this should be our main agenda before we will go to this process. So, now you come back to the original position. What is this actually structure? So, our objective is here to test the R square, whether R square is statistically significant or not. So, for that we have to prepare the ANOVA tables. Okay. So, we have to prepare the ANOVA table, just like in the first objective. In the first objective we have explained here, if the first objective what we have explained here. Yes, this is what the first objective we have explained here. The first objective here, the fitness of the model is like this. So, we like to know the target component is T alpha hat and the target component is T beta hat. Okay. So, now we have received here summation E square by n minus 2. So, that is what sigma square u. So, now variance of alpha hat you have. So, similarly, you have to go for standard error of alpha hat. Standard error of alpha hat is nothing but variance of alpha hat. Okay. So, now similarly, what we have to do here? So, now we have to get the variance of beta hat here. Variance of beta hat is nothing but sigma square u by summation x square. Okay. So, similarly, standard error of beta hat is nothing but square root of variance of beta hats. Okay. So, this is what the beta hat parameter structures and alpha hat parameter structure is. You can say that means standard error of alpha hat is nothing but sigma square u summation x square by n summation x squares. Okay. So, this is what the structure, this is standard error of these items. All right. So, now okay, standard error of this much. So, what you have to do? So, once you have alpha variance of alpha hat, you can get the standard error of alpha hat. So, what is the issue here? So, now our objective is to know whether alpha hat is significant or beta hat is significant or beta hat is significant. So, we need to calculate T of alpha hat and you need to calculate T of beta hats. Okay. So, for this to know the significance of this particular alpha hat and beta hat, so we have to apply a statistical hypothesis, or we have to use the statistical hypothesis. Basically, the statistical hypothesis is divided into two parts called as a null hypothesis and alternative hypothesis. So, this is null hypothesis, then in contemporary to null hypothesis we have alternative hypothesis. So, we start with the null hypothesis, that the suppose our target is to test alpha is significant. Alpha is significant means alpha must have some value. Okay. If alpha has some value, then we on the basis of that value we have to test the significance. So, now let us we start with that alpha is equal to 0. Okay. So, alpha H 0 usually fit that alpha equal to 0. Let us say alpha equal to 0, and we have to test alpha not equal to 0. So, once you reject this null hypothesis, then we are in the right track. If you could not reject, then that variable may not be statistically significant. So, that means, so T of alpha hat is basically we will calculate technically is nothing but alpha hat by standard error of alpha hat, and T of beta hat is nothing but you can say beta hat by standard error of beta hat. Okay. So, now this is calculated statistic, this is calculated statistic, that has to be compared with tabulated statistic. Okay. So, this has to be also compared with tabulated statistic. Then we get to know whether this particular item is statistically significant or not, and if it is significant, at what level they are significant. So, we have different structure of significance level that we in fact we have discussed in the last class. So, there are 3 levels 1%, 1 tail and 2 tail, 5% 1 tail 2 tail, and 10% 1 tail 2 tail. So, the starting procedure is we have to start with the 1% level, then if it is not significant, then you have to move to 5%, if it is not significant 5%, then you have to go to 10%. But if you will get significance at 1%, then that means your model accuracy is very high, and the reliability of the model is also, that means the reliability of the model is perfectly okay. Okay. If we are getting significance at the 10% levels, yes, model is reliable one, but the degree of reliability may be very less. So, when the variable is statistically significant close to 1 or at the level of 1%, then obviously the model reliability or model accuracy is very high or absolutely okay. So, now we will target, or we have to reformulate, or we have to design or redesign in such a way, so that the parameters means involved in this particular systems, modeling systems should be highly significant, highly statistically significant, and mostly it should be at the level of 1% only. If it is so, then the model reliability for so far as a first order condition is okay. Now, again for sufficient condition we have to go for R square part. That means, there are 2 problems here. So, your all parameters should be statistically significant at the higher level, means preferable at 1% level, and same times your R square will be also statistically significant at the 1% levels. Okay. That is at the higher levels. If it is so, then the model is absolutely fit for the forecasting, but the problem is if parameters are significant and R square is not significant, or R square is significant, parameters are not significant, then the problem is very complicated. So, that means, there is some kind of fault or problem in between this process. So, that process has to be investigated further again. There are certain problems in between, so that we are getting first part and we are not receiving the second part. The system will be very much okay or perfectly okay when parameters are significant, it should be R square should be statistically significant. If not, then there is a serious issue for this particular estimated model. We have to redesign, or you have to rebuild till you get the best fitted models, where both parameters are statistically significant and your R square will be statistically significant. So, we will discuss details in the next class. Thank you very much. Have a nice day.